Hi class, welcome to chemistry. I want to talk about measurements in the laboratory. Even though this is discussing measurements in the laboratory, it also applies to questions that could be asked during the lecture. I want to explain how you would read an Erlenmeyer flask. This is an Erlenmeyer flask. This is a volumetric flask, a beaker, a cylinder, based on the tick marks. The lines that are drawn on whatever instrument you're reading are called the tick marks. So one of the things that you're going to have to memorize for your second quiz, not your first quiz, but your second quiz, so for next week, week 3, is you're going to have to memorize the SI units and the prefixes, mega, kilo, hecto, deca, deci, centi, milli, micro. And it goes down lower in your textbook. It's going to be table 2.2 or 2.3 depending on your edition. And it will just be called prefixes, and I'll also post it under announcements, but you're going to have to memorize it for week 3 because as nurses you're going to use these a lot. Notice that hecto, kilo, and mega are large values. Even deca means values of 10. And then when they start to have I's or O's, deci, centi, milli, they're less than 1 values, and they tend to go in increments of 3. So micro, which is this little mu here, is 1/1,000,000th. In nursing, they call it an MC. Grams in nursing, they don't use the symbol G. Always they use GM. So a microgram in nursing might be written as MCGM. But here you can see the SI units. It's common for them to make this mistake. There's actually a typo here. Right here it says that the SI unit, which is the International System of Units that they should be using worldwide, are grams, but it's actually a kilogram. Everything else is correct though. For length it's meter, for temperature it's Kelvin, time is second, amount we'll learn later on is mole, electrical current we will not learn, nor will we learn luminous intensity. But remember that mass is kilograms. So significant figure rules. A significant figure is really important. It's really important that you don't round in healthcare or in the chemistry laboratory because you want as many significant figures as you can because that shows your precision. That shows that you were careful in taking your measurement. So here are the rules in one table. Digits 1 to 9 are always significant. So in the example 9,845, there's 4 significant figures. Zeros between the digits, it means they were measured, but it came out to be 0. Your book calls it captured zeros or captive zeros. Same thing as zeros in the middle. So 4,102 also has 4 significant figures. Then decimal places determine significant figures for everything else with a 0. So zeros right of a decimal place are always significant, except they're missing one little rule that they should have added on. That as long as there's a real number. So as soon as there's a real number that starts here, these are all significant. These are zeros in the middle, they count. Real number after the decimal, so any 0 after real numbers after the decimal, they count. So the total number in here are 5 significant figures. Now when you have a number that doesn't have a decimal, which isn't good because they should be written in scientific notation to tell you how many significant figures, but in real life it occurs that you have numbers without decimals, then that means you can only consider these 2 as significant. So if I said where is the uncertainty, it's right here, it's at the hundredths place. You'd say the 2 mark is the uncertainty. And then total number of significant figures that we know for sure are 2. When you have zeros to the left of a decimal and there's no number in front or anywhere in between, they don't count, they're just placeholders. It's like you are weighing something really lightweight, a gnat for example, and it didn't have a mass, so there's nothing to be measured here. So your measurement started here, and that gives you 4 significant figures. With addition and subtraction, and we'll talk about this more in my teach back in class, but you had a little bit in lab, the value with the least amount of decimal places is the amount that your final answer has. So this one goes to the hundredths place, this one goes to the tenths. Your answer can only go to the tenths. Or same for subtraction. This one goes to the hundredths, this one goes to the tenths, so your answer can only go to the tenths. Notice it doesn't matter that you have 2 sig figs here and you still end up with 3. The fact that you have 2 sig figs here and end up with 2 is coincidence. You're really just looking at places after the decimal with addition and subtraction. Multiplication and division are much easier because you just look at total sig figs. Since there's 3 sig figs here and 1 here, your answer can only have 1. Since this is 0 doesn't count, it's 1. Or they could say 5 times 10 to the 1. Division's the same. 3 sig figs here, 2 sig figs here, so your answer is rounded to 2 sig figs. So measuring with tick marks. Sometimes that can throw people because there are different tick marks on different things. Like a graduated cylinder, a little one may have more tick marks, a large one may have less tick marks. So you look at the tick mark and you go one place beyond. So if this graduated cylinder measures 1 milliliters, you write it to the tenths place. So beakers are the least accurate instrument for measuring volume. Those are just good for storing liquids. Graduated cylinders are better, and that's typically what we use in the lab. Volumetric flasks are expensive, and they're so precise, see the little line right here, that they use them when they want exact amounts. You may see these in the hospital with the medical technician because they need exact amounts. Erlenmeyer flasks, which looks like this, it's narrow at the top, chemists like to use because they can swirl them and they tend not to splash. Or they can heat them and there's less vapor being released because it's narrow at the top. But they are not good for measuring, same as the beaker. Pipettes are the best for measuring. This is an Eppendorf, which they typically use in a biochemistry laboratory. It has a plastic tip, so they often don't use it in a chemistry laboratory because many of the organic liquids will eat that plastic tip. But in a hospital, you oftentimes are using water, so you'll see these Eppendorf pipettes, and they are very accurate, and they read them here. Sometimes they're digital, sometimes, again, it's tick marks. So, accuracy versus precision. Accuracy is the nearness of a measure to the true or accepted value. For example, the density of water at room temperature is 1 gram per milliliter, which means 1 gram equals 1 milliliter. If you measure the density of water at room temperature and you get that, then you are very accurate. Precision means that you get the same value over and over again, but it may not necessarily be the true value. You're just getting the same value. This tends to happen when one of your measuring tools needs to be calibrated, so it's off a little bit. So you keep getting the same amounts if you're doing your measurements properly, but for example, to go back to the volumetric flask, if it gets warped because it's been in an oven, it's no longer accurate, but it's always going to give you a similar answer, a precise answer. So here is what I really wanted to show you, because this is what people have problems with, and it's measuring using tick marks. So the first thing you have to ask yourself is, what is this tick mark reading? If the tick mark is reading to the ones, which it is here, it looks like, because it's going up to 20 and then 21, 22, 23, 24, 25. Sometimes you have to count. You read the bottom of the meniscus. You get a meniscus with water because water has surface tension, so it kind of sticks to the sides. But reading the bottom, statistically, is most accurate to the true value, or the accurate value, of the actual liquid in the flask. So if you were to read this, since it's reading to the ones place, you would write it down to the tenths place. So you wouldn't write 20 milliliters, you'd write 20.0 milliliters. If you saw it dip a little bit lower, let's say it evaporates over time. Now it's halfway in between, 19.5. But notice that when it's at 20, you don't just say 20, you still say 20.0, because that tells someone who just looks at this number that you used a cylinder that measured to the ones place because you wrote down the tenths place. And then here's a little fun fact. 1 drop of water is about 50 microliters. Very small. We'll start doing these conversions, and you'll see just how small that is. So measuring mass. In chemistry, we use a balance, and this particular balance goes all the way to the tenths, hundredths, thousandths, 10,000ths place. You write it all down. Your uncertainty is right here, the 5. It's always the last digit. This 0 doesn't count. Whatever they were measuring, it didn't have a mass. But when you are measuring, you want to make sure that your balance is clean, particle-free. You want to make sure that they say both sides of the top glass doors are shut. These are for really accurate balances. We have what you call top loaders, meaning they don't have the glass doors. But the doors help to prevent fluctuations in air current, so these are really exact. You want to then tare it or hit 0, make sure it's 0. You want to use the same balance throughout your entire laboratory. And you want to make sure that it's stable, so the number's not bouncing around. Sometimes that's just someone hitting the lab bench, and you just need everyone to like be calm, and then you hit 0, and then you always place your sample right in the middle because it has the most accurate reading in the middle. Here's some sources of uncertainty. So there are some procedural limitations. For example, the next lab that we do will involve coffee cups, and some heat can escape those coffee cups. Instrument limitations, maybe the balance hasn't been calibrated and it's off just a little bit. So what you have to ask yourself is, did I do it properly? Did I follow the directions? If you're using a ruler and you're measuring in centimeters, centimeters always reads to the tenths place on a ruler, so you always have to write it down to the hundredths place, always, always on a ruler in centimeters. Was the instrument used correctly? Are you using the same balance over and over again? You typically want to use the same tools throughout an experiment so that you do not insert different error in case the instrument is a little bit off. It's the same error throughout. Did you use the correct reagents? Was the good technique used? And did you do proper significant figures with your calculations? Because you'll always be doing significant figures. So unpredicted or unforeseen changes in the procedure or experiment, these are random errors. They're unavoidable. To avoid them a little bit, or to minimize them, I should say, you want to use high quality laboratory equipment, so don't measure volume with a beaker, use a cylinder. If you have pipettes out, use the pipettes, and use consistent technique, so be careful. Poor precision of the apparatus means that it wasn't calibrated correctly, and you can't really control that always. Imperfect experimental procedures, so you're not reading the meniscus, it's reading to the tenths place, but you're not writing down to the hundredths, or it's reading to the ones, but you're not writing to the tenths, or maybe it reads to the tens, in which case you'd write to the ones, or imperfect judgments by the operator. So these are things that you want to check.